Welcome back. All right, today we'll be talking about related rates. We will go through the steps to solve them, and then we will go through 3 example problems. Okay, so here are our steps to solving a related rate. Step 1, always draw a picture. Okay, after we draw our picture, we want to define our variables. All right, what do we have and what are we looking for? All right, next step, what are our known equations? A lot of times it's geometric, Pythagorean theorem, volume of something. Otherwise, we just got to find out, what can we derive from to get our answer. Then we derive using implicit differentiation, and then we solve for our solution, whatever that might be. Whether we need to find a length, a rate, we kind of figure out what we need to solve, derive implicitly, and then we go for it. Okay, example 1. Water leaking onto a floor forms a circular pool. The radius of the pool increases at a rate of 4 centimeters per minute. How fast is the area of the pool increasing when the radius is 5 centimeters? Okay, so step 1, like we said, draw a picture. All right, we're forming a circular pool here, so I will draw a simple circle. We want to investigate when the radius of this pool is 5 centimeters. And that's about it for what we got right now. All right, so now we have to find out what we know, what we don't know. What are we looking for? All right, this thing is going to have an area. It's going to have a radius, and we're looking at 5 centimeters. Okay, we have the rate of the radius increasing, which is 4 centimeters per minute. All right, so that's change in radius with respect to time, so we'll call that dr over dt and set that equal to 4 centimeters per minute. Okay, so that's pretty much all we have. Now we go into given equations. Well, we know that the area of a circle is equal to pi r squared. Oh, I forgot what we were looking for. We're looking for how fast the area of the pool is increasing. So how fast is our area changing with respect to time? Okay, so now we have our known equation. Step 4 is to derive implicitly. In this case, it's with respect to time, dt. So our derivative of a is going to be dA over dt, and that is equal to 2 pi r. The 2 comes down for the power rule. That goes to 1, and all of that times our dr over dt. Okay, so we are looking for our dA over dt. We have our constant 2, constant pi, our radius of 5 centimeters, and we also have our dr dt of 4 centimeters per minute. We multiply that all together, and be very careful with your units. We have 40 centimeters, 2 centimeters, so we have centimeters squared per minute. All right, and that's your dA over dt. There you go. Example 2. A conical paper cup is 10 centimeters tall with a radius of 10 centimeters. The cup is being filled with water so that water level rises at a rate of 2 centimeters per second. At what rate is the water being poured into the cup when the water level is at 8 centimeters? Okay, so for this example, we have a conical paper cup. So our step 1, always draw the picture. So I got my cup here. I know that this cup is 10 centimeters tall. Call that H. It also has an and a radius of 10 centimeters. Okay, so our cup is being filled from the bottom so that the water level rises at a rate of 2 centimeters per second. And we want to know at what rate is water being poured into the cup when the water level is at 8 centimeters. So going along with finding what we want to know, and what are we looking for, we have that the water level rises at a rate of 2 centimeters per second. So we'll call that our dH over dt, 2 centimeters per second. We're investigating here when the water level is at 8, so I would say H is equal to 8 centimeters. We have our H of the cone, which is equal to 10 centimeters, which is equal to our radius of the cone, or conical cup, if you want to keep it in terms of that. Okay, we are looking for our rate that the water is being poured into the cup, so that is a rate of volume. So we want to find dV over dt. All right, and then we go into our known equations. So the volume of a cone is equal to 1/3 pi r squared h. All right, and this is where we kind of run into a problem, because I know that I might need a product rule for r squared times h, and I don't really have a dr dt. So here's where we can kind of, for this particular cone, relate our height and our r. So r is equal to h in this case. So we can rewrite this as 1/3 pi h to the third. So now we differentiate this implicitly, and we look for our rate of volume at 8 centimeters. So dV over dt, I leave the 1/3 pi off to the side. Bring down the 3, change that to a 2, 3h squared, and that's all times your dH over dt. Okay, your 3's cancel out, and then you're left with pi h squared times dH over dt equals your dV dt. All right, and then we just plug in. So this is going to equal pi times 8 centimeters squared times 2 centimeters per second. Centimeter squared times another centimeter will give you pi times 128 centimeters cubed per second. And that's it. And here's our last example. A ladder 10 meters long is leaning against a vertical wall with its other end on the ground. The top end of the ladder is sliding down the wall. When the top end is 6 meters from the ground, it is sliding down at 2 meters per second. How fast is the bottom moving away from the wall at that instant? All right, so for our ladder problem, we have a ladder that is leaning against a vertical wall. So we have our ladder here, 10 meters, and it is leaning against a vertical wall with some distance here away from it. We're looking for when the top end is 6 meters away from the ground. All right, I'll call that my y side. Call this my z side. And then we know from Pythagorean's theorem that 10 squared minus 6 squared would give you 8 squared. So then I have 8 meters right here. Call that my x side. All right. As far as knowns and unknowns go, we have our x equals 8 meters. over y equals 6 meters, z equals 10 meters. We know that when we're at 6 meters, the ladder is sliding down at a rate of 2 meters per second. So dy over dt is equal to -2 meters per second. Our dx over dt is what we are looking for. When it asks us how fast is the bottom moving away from the wall at that instant, we are looking for our dx dt. And since our ladder stays at 10 meters, right, there's no change there. So our dz over dt equals 0 centimeters per second, I guess you could say. All right, so then we go into our known equations. Well, this is a simple Pythagorean theorem. X squared plus y squared is equal to z squared. We derive this guy implicitly, so that would be 2x times dx dt plus 2y dy over dt equals 2z dz over dt. All right, so I have a 2 in every term, so I can cancel those out. And then I am stuck with this. So since we know that our dz dt goes to 0, we can get this out of here. And that is equal to 0. Okay, and then we can start plugging in. So I will have 8 meters times dx over dt is equal to 6 meters times -2 meters per second. 8 meters times dx over dt gives me -12 meters squared per second. Oh no, if we move that over, that would be positive. Oops. Because I subtract the y over, and that was already negative from our dy over dt. So then I just divide out my 8 meters. So then dx over dt equals 12 over 8 meters per second, or you just divide out your 2. Oh no, you divide out a 4 in this case, and you get 3 over 2 meters per second. And that is your answer. That is how fast the ladder is sliding away from the wall at that instant. And it should be positive because our dy dt is going down, then our dx dt is going out. So those numbers should make sense.